So for the first one, we have to first of all find delta S, because we need to work out what Gibbs free energy is. So delta S for this reaction, so delta S for the system is going to be, remember, the sum of S stand for the products minus the sum of S for the reactants. To do that, my products, if I have a look, I've got minus 192, so it's 2 times 192 minus my reactants, which is going to be 3 hydrogens, 3 times 130, plus a nitrogen, which is 192. And if you work that out, I think you get minus 198 joules per mole per Kelvin. Okay.
And then you divide it by 1,000.
Yeah, well that's fine for delta S. Then to use it in Gibbs free energy, they've asked me to calculate Gibbs free energy at, it was 25 degrees C, wasn't it? Now remember, 25 degrees C is 298 Kelvin. So to do that, delta G is going to be delta H minus T delta S. Delta H, they told me, is minus 92. The temperature is 298, and I need to times that by delta S, but I need to divide this by 1,000. So this is in joules, whereas this is in kilojoules. So that becomes minus 0.198. And if I do that, I think the answer comes out to be minus 33 kilojoules per mole. So, is the reaction feasible at 298 Kelvin?
Yeah.
Yes, it is, because I have a negative delta G. They then asked me to calculate the temperature at which delta G is equal to 0. So that's that's a temperature which is a borderline between it being feasible or unfeasible. So delta G we're going to set is now 0. So 0 equals delta H minus T delta S. Delta H is minus 92 minus the temperature times delta S, which is minus 0.198. So minus 92 plus 0.198 times T, because I've got a minus and a minus there. If I rearrange that, I know that 92 is equal to 0.198 T, so T is equal to 92 divided by 0.198, which comes to 465, right up to nearest Kelvin. In degrees C, I needed minus 273. So if I do that, that is equal to the temperature is equal to 192 degrees C.
Sorry, how do you convert?
Okay, to convert, I minus, so to convert, whoops, Kelvin to degrees C, you minus 273.
Always, whatever it is.
Yeah.
And so it's 2730.
That's right, yeah. 273 degrees C. No,
So
sorry. Minus 273 degrees C is 0 Kelvin.
Okay.
Right. So they then asked me, well, what will be the effect of raising, what will be the effect of temperature on that? Let's have a look. If we go back to the table that we did last time, I have got a negative delta H, and I have a negative delta S. So if you refer to your table that we did last time, a negative delta H and a negative delta S, that means that as I increase the temperature, it becomes unfeasible.
At a high temperature.
So above 192 degrees C, it becomes unfeasible. Below 192 degrees C, it is
So
feasible.
that's the temperature in which it's feasible.
That's my
What we
cusp.
have to work out.
Yeah, so anything above, for this example, anything above 192 is what I would call a high temperature, and below I would call it low temperature. When I'm using it.
Every time you work out.
All the time it's different. So we're going to do the same thing. What you can do is, always think, is it a sensible answer that you're getting? So I've got one gas mole becoming 2, so I'd expect the sign of entropy for the system to be positive, wouldn't I? Because it's becoming more disordered. But let's have a look. Delta S for the system is now going to be the sum of the products, which is 220 plus 189 minus my reactant, which is 161. So if you do that, so 220 plus 189 minus 161 is equal to, do we get
That's
to
kilojoule.
248?
Yeah.
Joules per mole per Kelvin. I'm then going to work out delta G. Delta G is going to be delta H minus T delta S. Delta H, they told me, is 87. The temperature they want me to do it is at 25 degrees C, which is 298 Kelvin. Delta S is 248, but I need to divide that by 1,000 to give me 0.248. And if I do that, let's do that times 0.248. That's 87 minus 61.5?
No.
No.
You've even got a calculator.
I know. 298 times 0.248. 73.9?
Yeah.
Get out the calculator. So 87 minus, let's call that 74. That gives me 13 kilojoules per mole. So is it feasible?
No.
No, it's not feasible at 25 degrees C. So let's find the temperature which it is feasible at, which means I have to set delta G to equal 0. So we're now going to do delta G equals 0. So delta G equals 0. I have 0 equals delta H minus T delta S. You can just rearrange that straight away to give you T delta S is equal to delta H by just moving that over that. So T is equal to delta H divided by delta S. Delta H is 87. Delta S I copied off the board.
0.284.
Brilliant. 0.248. Brilliant. So let's do that. 87 divided by 2.248. That equals 351 Kelvin minus 273, which is going to equal 78 degrees C. So, what happens if I increase the temperature? Well, delta H is positive, delta S is positive, so as I increase the temperature, the reaction becomes
Feasible.
it becomes feasible. Yeah. If you look on your table,
Sorry, I was reading off the wrong.
yes, both are positive. So as I increase the temperature, so above 78 degrees C, it is feasible. Which makes sense because we just found out that 25 degrees C was unfeasible, didn't we?
Yes.
Wait, so they're both unfeasible, but as you...
But if I carry on, this is the temperature at which it's at the cusp.
Mhm.
So 25 degrees, no way. 78, yeah, just about. So as I increase the
Increase it.
temperature, it becomes more feasible.
Okay.
Yeah.